In this lecture, we're going to review some geometry essentials. We'll start by talking about the Pythagorean theorem and its converse. The Pythagorean theorem states that in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So if we look at the picture of a right triangle, remember the legs are the two sides that make up the right angle, denoted A and B in this picture, and the hypotenuse, which is the longest side, is the side that is across from the right angle, denoted C in this picture. So, corresponding to the picture here, the Pythagorean theorem can be written as C squared equals A squared plus B squared. Now let's talk about the Pythagorean converse. The Pythagorean converse says, in a triangle, if the square of the length of one side equals the sum of the squares of the lengths of the other two sides, then the triangle must be a right triangle. So if the Pythagorean theorem holds, if we can show that C squared equals A squared plus B squared, then the triangle must be a right triangle. So let's look at an example using the Pythagorean converse. A triangle has sides of lengths 10, 24, and 26, and we want to determine, is this a right triangle? Now, since the Pythagorean theorem says that C squared equals A squared plus B squared, that is, all of the terms are squared, let's go ahead and square all of the lengths of these sides. So 10 squared is 100, 24 squared is 576, and 26 squared is 676. Let's see if this matches up with the Pythagorean theorem. So remember, with the Pythagorean theorem, we're looking at C squared equals A squared plus B squared, where C is the longest side. So for our problem, our C would be 26. So does 26 squared equal 10 squared plus 24 squared? And if we put that together, 26 squared is 676, 10 squared is 100, 24 squared is 576. 676 does equal 100 plus 576, so this shows that this is a right triangle because it matches up with the Pythagorean theorem. Let's look at another example. We're given that a triangle has sides of lengths 2, 2, and 3, and we want to determine, is this a right triangle? Take a few minutes and try to work this out yourself. When you're ready, continue the lecture. So, to determine whether or not this triangle is a right triangle, we need to see if the Pythagorean theorem is true. Does C squared equal A squared plus B squared? Again, C is always going to be the longest side we're given, so we want to see, does 2 squared plus 2 squared equal 3 squared? We can simplify all of these values. 2 squared is 4, 2 squared is 4, and 3 squared is 9, so we have 4 plus 4 equals 9. And if we simplify that, we get 8 equals 9, which is obviously not true. So, this triangle is not a right triangle because the lengths of its sides do not satisfy the Pythagorean theorem. Next, we want to talk about using geometry formulas. First, we'll look at formulas dealing with a rectangle that has length L and width W. The area of a rectangle is equal to length times width, and the perimeter is equal to 2 times the length plus 2 times the width. For a triangle with base B and altitude h, we have that the area is equal to 1/2 times base times height. For a circle with radius r, where the diameter is equal to 2 times r, we have that the area is equal to pi times r squared, and the circumference is equal to 2 times pi times r, or pi times d. For a closed rectangular box with length L, width W, and height h, we're given that the volume is equal to length times width times height, and the surface area is equal to 2 times length times width, plus 2 times length times height, plus 2 times width times height. For a sphere of radius r, we're given that the volume is equal to 4/3 pi r cubed, and the surface area is equal to 4 pi r squared. And then finally, for a right circular cylinder with height h and radius r, we're given the volume is equal to pi r squared h, And the surface area is equal to 2 times pi times r squared plus 2 times pi times r times h. So let's do an example. Find the volume and surface area of a rectangular box with length of 9 inches, width of 4 inches, and height of 8 inches. We'll start by finding the volume. So from the formulas that we just reviewed, volume is equal to length times width times height, so we just need to plug in the numbers that we know. Plugging in the values we know for length, width, and height, we'll have volume equals 9 times 4 times 8. If we multiply 9 times 4, that's 36, so volume will equal 36 times 8. And 36 times 8 is equal to 288, so our volume will be 288 cubic inches. Next, we'll work on the surface area. So from the formulas that we were given, the surface area of a rectangular box is 2 times the length times the width, plus 2 times the width times the height, plus 2 times the length times the height. Again, we just need to plug in the values that we know. Plugging in the values for length, width, and height, we're going to have that our surface area is equal to 2 times 9 times 4, plus 2 times 4 times 8, plus 2 times 9 times 8. And if we simplify the multiplication above, we would have 72 plus 64 plus 144. Add those together and we'll get that the surface area is equal to 280 square inches. For another example, we want to find the area of the shaded region. So if we look at the figure that's given to us, we have a square that has legs of length 2, and a circle that's inscribed inside the square. So if we think about this, the area of the shaded region will be equal to the area of the square minus the area of the circle. Using the formulas for the area of a square and the area of a circle, we'll have the area of the shaded region is equal to the length times the width of the box minus pi times the radius of the circle squared. So we know that the length and width of the square are both 2, and that the diameter of the circle also is going to be 2, so the radius would be 1. If we plug those values into the formula we have, we'll get a equals 2 times 2 minus pi times 1 squared. And if we simplify that, we'll get a equals 4 minus pi, and the area is measured in square units, so 4 minus pi square units. Next, we want to talk briefly about congruent triangles. Two triangles are said to be congruent if each of the corresponding angles is the same measure and each corresponding side is equal. We have several ways to determine whether or not triangles are congruent. The first way is called the angle-side angle case. So if we're given two triangles and two of the angles and the side in between those angles are the same on both triangles, then those two triangles must be congruent. We can also tell triangles are congruent using the side-side-side case. So that says that if all three sides of both triangles are the same, then the triangles must be congruent. And finally, we have the side-angle-side case, which says that if two sides are the same and the angle between the two sides are also the same, then the two triangles must be congruent. Finally, we want to talk briefly about similar triangles. By definition, two triangles are similar if the corresponding angles are equal and the lengths of the corresponding sides are proportional. And we have a couple of different ways to determine if triangles are similar. The first is called the angle-angle case. So if two angles of any triangles are the same, then those two triangles must be similar. Next, we have the side-side-side case. In this case, it says that if all three sides of the triangles follow the same proportion, or if all three sides are proportional, then the triangles must be similar. So in the picture shown, notice that the sides of the small triangle are 10, 5, and 6, and the sides of the big triangle are 30, 15, and 18. Well, if you multiply each side of the small triangle by 3, those will give you the sides of the big triangle. So if you can multiply the sides by the same number, then they're proportional. And finally, we have the side-angle-side case. That says that if two sides of a triangle are proportional to the same corresponding sides of another triangle, and the included angle, or the angle between those sides, are the same in both triangles, then the two triangles must be similar. So we want to do an example where we're going to use similar triangles. If we're given that the pair of triangles shown here are similar, we want to find the values of x, capital A, capital B, and capital C. We'll start by identifying the measure of the angles A, B, and C. So these triangles are similar. That means that the measure of the angles will be the same between the two triangles. We just need to match the corresponding angles together. Fortunately, the triangle is oriented in the same direction on both triangles, so the acute angle on the right, the 30-degree angle in the big triangle, will be the same as A, so that tells us that A is a measure of 30 degrees. Similarly, B, being the angle in the upper left, will match up with the 75-degree angle in the larger triangle, and C, being the angle at the bottom of the triangle, will match up with the 75-degree angle in the larger triangle. Now the last thing that we need to do is find the length of side x. Remember, the sides of similar triangles are proportional, so if I set up a proportion of the sides to the two triangles, it should equal regardless of which side we're looking at. So I know that the side between B and C is 6, and the corresponding side in the large triangle is 12, so if I make that ratio 6 over 12, the same can be done with the other sides of the triangle. So on the small triangle, we have length x, and on the larger triangle, the corresponding side is 16, so we could create the same ratio, x divided by 16, and since the triangles are similar, those two ratios must be equal. 6 divided by 12 must equal x divided by 16, and so we can solve this equation for x. First, we can simplify. 6 over 12 would be 1/2. And then to solve for x, to get x by itself on the right-hand side, we can multiply both sides by 16. So 16 times 1/2 will equal x. And if we simplify that, 16 times 1/2 is 8. So the length of x is equal to 8.